Okay. Turn off the camera's having trouble. Yeah. Okay. Cool. All right. Let us learn. Okay, last thing we did, just in case you forgot, it's been a little while. We talked about polar coordinates and we graphed 4 points, and then we translated back and forth between, well, actually just from polar to rectangular coordinates. And I told you this will be important, and x squared plus y squared equals r squared is important. Okay, and then we did those two, and then we didn't graph any polar function. Which is important for sure for what you're going to get asked on the test. Or at least kind of it is. You're not going to get asked to graph the polar function. Most of the questions that I've seen on polar functions give you the graph, but it's just good to verify. Like they're going to ask you to get the area within the polar function, and it's good to verify. Like, should the bounds be 0 to pi, or should they be pi to 3 pi, or something like that. So it's just good to know how to verify and how to check what part of the graph is what. So okay, let's graph these two functions. They're not super complicated, but they like if you haven't thought about how to graph polar functions, it's kind of tricky. But here's the way I know how to do it. Maybe you guys did it differently in pre-calculus. Like maybe they know some tricks that I don't. But I just know to make a table and then like plot the points accordingly. So 1 plus sine of theta, I would just do this. I would say here's theta, here's the radius. And then I would, in this particular case, since I don't see anything messing with the period or anything like that, I would just choose maybe the easy point on the unit circle from 0 to 5. If this had been like sine of 3 theta or something, then maybe I'd choose 3 times as many points just to see, or go 3 times as fast through the unit circle so that I get one good full cycle. But you'll see what I mean if we ever see one. But for here, 1 plus sine of theta, that's kind of almost the most normal function you can have. If it was sine of theta, that would be like even more normal. But anyway, what I'm saying is, let me just choose some easy points here, like 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then if I'm like, oh, actually, I don't know what that looks like, then I'll choose more points, like pi over 4 in between all these or something. But for now, let's choose these and see if we get an idea of what the graph looks like. So watch this. Plug in 0, I get 1 plus 0, so 1. Plug in pi over 2, I get 1 plus 1, so 2. 1 plus 0, so 1. 3 pi over 2 would be negative 1, so 0. And then 2 pi would be 0 again. Oh, 1 plus 0, so 1. Okay, cool. And then I might plot these points. So theta being 0, r being 1 would be here. And then pi over 2, 2 would be here. And then pi 1 would be here. 3 pi over 2, 0. I just remember that I got to go back to the pole, like to the origin is what they call it. In polar coordinates, the origin is called the pole. And then 2 pi is back to 1. So the idea is you start here, and then as you rotate, you're increasing to here, decreasing to here, decreasing, and then increasing. Yeah. So the shape will look something like this. Decreasing to 0, and then increasing back to 1. Oh, squiggly, like you went past and you went here?
Yeah. Like that.
That might be, if you're not sure, that might be a time. Jeremy's saying did something like this. In which case, yeah, that might happen. But I don't think it does in this case. But if you're not sure, then plug in more points. Like that happened between 3 pi over 2 and 2 pi. So maybe we'll plug in like what something between the two. 3 pi over 2. Sure, yeah, let's do that. And see if we get a negative, then yeah, there. But I don't think that's the case because the biggest this can get is 1. So it's not going to get negative. But let's just check. 11 pi over 6, that would be a sign of 1/2. So 1 plus 1/2 is positive 1.5. And that's around where we have it, like more than 1. No. Because what I'm saying, well, I mean, okay, if you want to, you can check all of them. If you're like not super sure. But I'm seeing that the sign of theta is only going to get as big as -1, and as negative as -1 and as big as 1. So the least this could ever be is 0. But yeah, if you think this isn't enough points, I don't have a good idea what this looks like, then okay, plug in more. But yeah, the black graph is correct. Yeah, Kia.
We always 11 / 6.
Am I wrong? Oh yeah, because it should be negative. Yeah, 0.5. You're right. Yeah, I was just looking over here. I said, oh, okay, it goes down a little bit. But yeah, since it goes down, it's -1/2. So 1 minus 1/2 is 0.5. You're right. Good job, Keaton. Good job. Yeah, 0.5, but still positive. So we kind of actually did this a little bit wrong. The black graph would look more like, I need to erase the whole thing, but start at 1, increase, decrease, go towards 0, at 11/5/6, you should be at like 1/2, so there, and then there. Yeah, that's a little bit more accurate. But okay, that's the idea for all of these. Sometimes what people do, and I didn't do this because I didn't want to make 2 separate graphs, but sometimes people graph this as if this was y equals 1 plus sine of x. Which here, let me show you just real quick. If you like it, then do this every time. But I don't like making 2 graphs just to make the one correct one. But sometimes they'll graph it as if this was y equals 1 plus sine of x. Obviously, these points would still correspond. This would be x, this would be y. And so your y equals whatever x graph would look something like this. Like this would be 0, this would be 2 pi. And so you can kind of see, well, something like that. Where this would be 3 pi over 2, this would be pi over 2, this would be pi, this would. And so the idea behind that is you can kind of see, okay, I'm going to start at 1, I'm going to get bigger, biggest I'll get will be 2, then I'll go back to 1, etc. So this might be helpful for some people. But like I said, I don't like making 2 graphs just to make the one, like make this graph first and then translate that into a polar one. Like, I think this is enough help, and I don't need to do the other graph. All right, that's that one question. Okay, cool. Then the other one is the same idea. Here's theta, here's r. 1 plus 2 cosine of theta. Okay, that one is a little bit more complicated because it's not just 1 plus cosine. It's not just cosine. It's not just 1 plus cosine. It's 1 plus 2 cosine. So I might need to plug in more points. In fact, I know I will need to plug in more points. But let me pretend I don't know that ahead of time and just plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, then here's me checking real quick. 1 plus 2 is 3. 1 plus 0 is 1. 1 minus 2 is -1. 1 plus 0 is 1. 1 plus 2 is 3. And then here's what I mean is that somewhere along the way I cross from positive numbers to negative numbers, and that would be a good spot to know. Like, when am I going to cross the pole and go into the negative direction? Like precisely when, not just somewhere between pi over 2 and pi. It would be good to know that. So let me plug in more points. And you can either just choose numbers between, like choose 2 pi over 3, 3 pi over 4, 5 pi over 6, and plug them all in and get a good idea what the graph is. Or you can do this and you can say, when am I going to cross the pole? In other words, when will this function equal 0 and change from positive numbers to negative, which is what I did on my key. Okay, and then here's us solving it. This is too fast, let me know, but here's 2 cosine of theta equals -1. Cosine, therefore, equals -1/2. Where does that happen on the unit circle? Oh, right here and right here, which would be 1, 2, 3, 4 pi over 6. Theta equals 4 pi over 6, which is, thank you. And then this was 4, 5, 6, 7, 8 pi over 6, which would be 4 pi over 2. I guess they're down here. Cool. Okay, so I know here I'm going to cross from positive numbers to negative numbers at, what is it, 2 pi over 3 here. And 4 pi over 3, which is here, which is between pi over 2 and 3 pi over 2 here. Cool. And if you want more points, then plug in more points and you get a better idea. Or do the thing where you make the XY graph and you can see it increases, then it decreases, and it crosses here and it becomes negative, etc. But I think this will be enough of this will give us enough of an idea. Like I said, on an AP test and on a lot of your homework questions, all you have to do is like they give you the graph and you have to verify, is this the right inner loop? Like, does the inner loop from 2 pi over 3 to 4 pi over 3, or is it from pi over 2 to 2 pi over 3? Like, all you have to do is verify and know how to check what part of the graph is what. So you don't need to do it a lot of detail in like graphing your own. Yeah, this one does have a loop. So 0, 3, boom, there it is. Pi over 2, 1, there it is. Then before I forget, let me go like this. So it starts as big as it gets, decreases, decreases, decreases to here. 2 pi over 3, when I get to this line right, before I get to that line right there, I should be getting closer to the pole. So whoop, like that. And when I get to 2 pi over 3, I should be right at the pole. And then I go into the negative numbers. So at pi negative 1, that would be, here's pi, and I go away from it. So I go this way, 1. So that all of these are going away, because all of these would be negative. So these will all go not towards the values, but away from the values. So it'll look something like that. And then, okay, that was pi negative 1. Then 4 pi over 3, I should go back from negative to positive. So what I mean is from pi to 4 pi over 3, I'm still on the negative side. So all of these are going to show up this way. But then by 4 pi over 3, which would be that line, then I should be back at 0. Like that. Nice. All right, cool. And then the rest is normal because all the rest are positive numbers. 3 pi over 2 would be 1. Pi over 2. 1. And then 2 pi 3. So back to here and out this way. Nice. And like I said, if you wouldn't have been able to make this graph on your own, like using just these numbers, then plug in more numbers yourself.
I remember there were some sort of tricks that you saw the equation exactly what type of like graph it would.
That I mean, just like you, I remember that that's a thing too, but I don't remember like if you see that this is bigger than this, then it's going to have a loop, or if you see that there's a 2 in here, then it'll be a heart or whatever. I don't remember that. But if you want to memorize that, then watch this. Here's a good segue. There's all the ones that you can memorize. What do you mean?
Just next to it, draw a graph and an example of it.
Yeah.
You don't have to.
Plug it into Desmos.
Yeah, I think that's what I wanted to do. That's why I was hesitating. I was like, do I want to draw it or do I not? Okay, yeah, let's do Desmo. That'll make it easier. All right, watch this. What time is it? 8:17? Dang, okay, good job. We're doing good on time. All right, so R equals A will just be a function. Well, it doesn't know what that is. Oh, okay, there we go. R equals number will just be a circle with a radius of whatever. That should make sense. R equals 8, R equals 7, R equals radius of whatever number you put here. So this will just be a circle. This one I think is also a circle, but like off to the side. So R equals, it says 2A, so like any even number, 4 cosine of theta. And that's a circle, but off to this, like, like not centered right at the center, but off to the side like that. To be sine of theta would be the same thing, but up here, the circle shifted upward, but not even shifted. It's like still touching the pole, just like resting on the x-axis, like for sine of theta, like that. If it was 8, it'll just be bigger, but still resting in the same place. I'm not sure why it says that it has to be an even number. I don't think that's true. Yeah, okay. But okay, anyway. And then that one, I actually don't remember what it looks like. 2 cosine of
Wouldn't it be
theta.
like in this, like a middle area for those two?
Oh yeah, that one is the equation of a circle with radius that a squared plus b squared. Centered at a comma b, I'm guessing. Yeah, there you go. Okay, and now I get why they said, because there's a relationship between this number and where it's centered. Whatever this number is, half of it would be the center origin. So this is another circle with somewhere else.
They're still typing that.
Mr. Porter.
Not always. No, if I make these big enough. I think it should.
Maybe choose the, yeah.
Well, looks like it might be.
Wait, is it that it's centered at
Yeah,
that
it's
point, or is that it just passes through it?
Centered at that point. Like, okay, let's say I want the center to be 10, 10, then 10, 10, 10, 10 would be 20 here and 20 there. So- And so the center is 10, 10.
Nice.
Boom. There you go. And then because of how big the radius is, I guess it will always pass through the axis, but it won't rest on it. You know what I mean? All right, cool. There's those. Then cardioids and I don't know how to say that word. That looks French. But okay, let's get rid of this. Okay, R equals A plus or minus. Well, let's do plus for now. B sine of theta. And then let's make little sliders. It says if A is B, then it's a cardioid, which is vaguely a heart-shaped graph, blah, 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 blah. Okay, so something like that. Or if it was cosine, then it'd be like a sideways part, like part this one. Okay. That. All right, if A is less than B, then you get an inner loop, which always contains the origin. So either this or sideways.
Cosine is sideways always.
Cosine is more x oriented and sine is y oriented. And then A bigger than B. This is a Limason. That's what I think. That's what the little c means.
Yeah. The special species that.
There you go. Anyway, it's that without an inner loop that does not contain the origin. I actually don't remember what it looked like.
Oh,
Oh, so it's like just a little divot. But not as hard shaped.
oh, there's a divot.
Yeah. Here, let's make this a cosine now. Yeah, side was one of those. Cool. And then the petals are, I think, the ones where you mess with the period. Yeah. You have a number outside and then a number inside. If n is odd, then the rose is n petaled. If it's even, then it's 2 n petaled. So A cosine
Even 1,000.
of n. Okay, and then what are we not using? B. Okay. So there is a one petal rose, but if we make it, whoa, crazy. We make it 2, then there's 4. If we make it 3, then it'd be 3 according to this. Wow, these are cool. Wow, look at these.
Well, it's in the points.
Right.
It's crazy.
So these are like the, you see the new one. No, I can't. That looks like good. Okay. How do you do a 3-1? Just like this. There.
Yeah.
Thanks.
It's going big.
Then A is how big it is, basically.
Okay.
Yeah. Here's 5, and so the biggest they'll get is 5.
Technically 4 points.
Yeah, kids.
It talks about being like odd or even, but what with the decimals, how does that?
Oh, yeah. I don't like
Because
effective.
yours is not even close to the amount. Right?
Yeah, I'm actually not super sure. This is what I was saying before. I don't have these memorized and I don't know.
That was cool.
But here's 3 and then 3.1. Three point one makes it crazy.
That's so cool. That is a clover. That is. That's a clover.
That's a,
I see a
Oh, I think
clover.
it's 10 in each one because it leads to like cash back.
Oh, that was amazing.
it's just like how many there are.
I don't know. That's something good for you guys to think about. Or I mean, I'll think about it later.
Right.
But I actually don't know.
Research paper.
I'm sure there's. Well, yeah, you write your own. Yeah.
Basic knowledge we have. Ah, there we go.
But this shouldn't be super, super incredibly deep, Matt. It's just it has something to do with the 4.7 and the period, and that normal period being 2 pi. So putting a 4.7 in here makes it 4.7 times as fast. But it probably has to do with the fact that like 2 pi and 4.7 are like relatively, like it probably has to do with their least common multiple or whatever. If n is even, then that. Yeah, I don't know. That's fun to think about, but I got to do it later. Because now I got to teach you about the calculus of polar coordinates. Which, yeah, so far all we've done is like graphing and converting and stuff like that. Yeah, which is technically not, it's calculus means like derivatives, integrals, that kind of stuff. So, we will start by finding tangent lines to polar curves. To do this, we will rely. I actually don't think I have to read this to you because I think your intuition will be good enough. But it says determine the equation of the line tangent to this polar graph. So just for fun, let's graph that polar graph. That'll be 3 plus 8 sine of theta.
No, highlighted.
Oh, r equals 3. R equals. Okay, so that. And then when pi is, or when theta is pi, so here, give me this tangent line. And you can see, okay, tangent lines are still what I know and love from way back in the day. I still need to get y minus something equals slope times x minus something. When theta is pi, that's a tough little guy to get. Well, I mean, it's not super obvious what this point is, and for sure it's not obvious what the slope is. But I think you guys can figure out, I mean, would you have any idea how to find the x and the y coordinate?
Yeah.
Into what? Well, into here, that would tell me what the radius is.
Oh, the derivative.
Well, yeah, but what if it had been like pi over 6? Okay, so then let me give you the general idea. In the case of pi, then yeah, it's kind of nice because pi is right on the axis. So whatever radius you get will be the x coordinate and the y coordinate will be 0. But in general, the general idea is to use the thing I was talking about before, where x is always r times cosine, y is always r times sine. So this one requires a lot of work, as you can probably tell from all this ugly fractions. You got to do in general. Find the x coordinate. Find the x coordinate and the y coordinate by using those little formulas. X equals r times cosine of theta. R being, oh shoot, this whole entire thing. So r equals 3 plus 8 sine of theta times cosine of theta. That, and then plug in pi into that. That will give you your x coordinate. And then this will give you your y coordinate, 3 plus 8 sine of theta times another sine of theta. Okay. And then if I plug in pi into these, I would get 3 plus 0 times cosine of pi. 3 plus 0 times -1, which is -3. And then y will be 3 plus 0 times 0, so 0. As we expected, like what I said, this is just directly sideways on the axis. So the x will have a coordinate, the y will be 0. Okay, so then that's good news. My x coordinate will be minus -3, or in other words, plus 3. And then y minus 0 here. Nice. And now the slope, again, the slope is the slope that you've learned like in 7th grade. It's rise over run. And so in other words, the change in y over the change in x. And so in other words, you want dy dx. So in the case, okay, in the case where it was y equals x, very easy, just take the derivative. In the case where it was x equals something of t and y equals something of t, a little bit harder, but just take this derivative over this derivative. Now we get to this one where y is this whole big thing and x is this whole big thing. So to get dy dx, you have to do derivative of this over derivative of this. And so it ends up being this big ugly thing. Okay, but it's ugly, it's tedious, but it shouldn't be super hard. Like in your brain, you should be thinking slope, dy dx. How do I do that? Oh shoot, yeah, I gotta take this derivative over this derivative. So hopefully conceptually that's not super hard, but like actually doing it can be annoying. Okay, but let's do it.
Why is it specifically plus or and minus on the bottom?
You'll see, it's because this one, the dx is going to have a cosine whose derivative is negative sine. So this will turn into a negative. But you'll kind of see where that comes about. And some people are good at memorizing this. I just always set up the equation and take the derivative and divide this by this. Because I'm not going to remember in a month or whatever your test is, 2 months. I'm not going to remember this particular formula, the r d theta times sine of theta plus r times cosine theta. I don't think I'll remember that, but I will remember to do dy over dx. So here's what I mean. Here's my dy d theta. And then the derivative of this would not be, it would not be 8 sine times cosine. Or sorry, it would not be 8 cosine times cosine. That would not be it because I'd be forgetting what? Yeah, product more like, because this is not sine of 3 plus 8 sine. That would be chain rule. This is this function times this function. So product rule. And product rule, do you guys remember that? Yay, good job. You guys, yeah. That would be okay. First left alone times the derivative of the second is cosine, plus second left alone times the derivative of the first. So that would be sine times a cosine. Okay, and then the x d theta, same thing. First left alone times derivative of the second. Times derivative of the second, which would be negative sine. Let me put the negative here. so it looks cleaner. And then second times derivative of the first, so plus second times derivative of the first would be a cosine. Nice. And then you guys, if you get theta equals pi over 4 and you need to plug that into here, then it can be really, really ugly because you'll get a bunch of radical 2's over 2's, radical 2's over 2's, and then simplifying that is a mess. So most of the time you'll see a pi over 2 or a pi here, but if they're being really annoying, then they'll give you a pi over 6 or something. But most of the time I see a pi or a pi over 2 because that's much easier to plug in. What's up? Negative 8 cosine. No, because this was the derivative of the first, which is the 8 sine.
Oh,
Okay. Okay. Oh, okay. Okay. Yeah, I kind of flipped these just to have them in order. The dy over dx. Okay, so then dy dx. Let me do two things at once. Let me divide these two and let me plug in the pi. Dy dx when theta equals pi equal to. Okay, let's do it. This divided by this, but plug in pi. So let me do it, a lot of it in my head. 3 plus 0 times cosine of pi is -1 plus 8 times -1 times 0, so 0. That's too much math at once. Okay. Good.
No, I wonder why you can't just cancel them out. Oh, wait.
Over -3 times 0, so 0 plus -1 times -8, so plus 8. Nice. Okay, let me make sure I didn't mess up any math in my brain. Let me make sure that's what I got on my T. But that would be our slope is -3/8. Yeah. Equals -3/8. Now this -3/8 go. Okay.
This is a calculator
Oh,
or
right, yeah, okay.
response?
I could see this being no calculator because we didn't really, in fact, we didn't really need a calculator. But if it was calculator, I guess it'd be kind of easier because you could say x equals this, pi equals this. Now take this prime, or sorry, pi prime over x prime and plug in pi. That would be nice, but I can see this being no calculator for sure. And don't let all this math like take away from the fact that you kind of already knew how to do. Give me the tangent line. Okay, y minus something equals slope times x minus something. Now I just need the x, which is r times cosine. I need the y, which is r times sine, and I need dy dx, which is dy over dx. That's all we did. It just took a while because it's so ugly. Cool. All right. And then 8:36. You guys leave in 9 minutes. Yeah, let me give you a preview. So area with polar coordinates. You're gonna get asked to find the. I mean, just like with normal functions, you're gonna get asked to find the area in a curve, basically. So with normal y equals x functions, it looks something like that, and you get the area between the curve and the axis. Okay. Well, with polar coordinates, since they're more circular in nature, and the rate and the like independent variable changes this way, you're gonna get asked like here's one of these. You're gonna get asked to find the area contained within the thing within the function, within the curve,
So
which is what this is saying.
But you still
that
set up
minus, yeah, isn't it that angle minus this angle minus that angle together?
Not really. Here, let me do a simpler one because I see what you're saying. Like, what about the inner loop that you just cut right over it? Don't worry about the inner loop yet. Here's a simpler function because they all work the same. But here's like a heart. Still the same idea. If I want the area between these two angles, that's kind of a circular one. Okay. So, oh yeah, what's up?
Would it be because like the inner loop's not part of that, like domain? Or
Exactly. No, yes, exactly. Good job. Yeah, okay. But if I want this area, hopefully you see like up here to get normal integrals, we set them up as a bunch of little rectangles. But here, like along the x-axis. But here, the nature of it is different because we're not going along the x-axis. We're changing like circularly. So this is more similar to, in other words, I'm changing, here's tiny changes along the theta direction, which is our independent variable when it comes to polar function. So here's tiny changes along the x-axis, independent variable when it comes to y equals rectangular functions, y equals x functions. These are tiny changes along the theta direction. So all I'm saying is the way that we get the area here is different than we get the area here. Here we just had rectangles, so height times width. Easy. Here you have to get areas of circles, or sorry, of sectors. Like slices of pie. These are the areas we want. And so the integral is going to look slightly different. So here, let me now write on the notes. Because of what I just said, we need areas of sectors, which is like slices of a circle. So if this was theta, or even better, you know, I said the tiny width was a dx. A tiny slice would be a d theta. Okay, if I were to get the area of this perfectly circular shape, then what I do is, do you guys remember how you get the area?
y over theta.
No, like forget about calculus. Like in geometry, do you guys remember?
To calculate the area of the full circle and then multiply it by the angle, or like the fraction of the angle.
Yeah, that's exactly it. Treat this like a fraction of the circle. So set up some sort of fraction, like proportion. So yeah, area of the whole circle would be pi r squared, whatever r is. Pi r squared. So it'd be pi r squared. And I set up the proportion. You can set it up in a bunch of different ways. Let me set it up in this particular case as area of the whole thing over the area that I want. Yeah, let's do that. Area of the whole thing over the area that I want equals, should be proportional to the slice that I am interested in, or no, sorry, the slice of the entire circle over the slice that I'm interested in. So this entire circle has an angle of 2 pi. So 2 pi is the whole circle over the slice that I'm interested in is just an angle of d theta. Nice, nice, nice. And then if you solve this for the area that you're interested in, like cross multiply and do all that, multiply by a, divide by this, multiply by this, you would get, let's just do one thing at a time. Pi r squared d theta equals 2 pi area that I want. And then divide by the 2 pi to get pi r squared d theta over 2 pi equals the area that I want. And so that's why on the next page, you'll see, oh shoot. You'll see the pi's cancel, 1/2 r squared d theta is the area that you want. And so that's why when they ask you find the area in this polar function, from 2 pi over 3 to 4 pi over 3, you don't just do integral of function d theta, you do this formula 1/2 r theta. All right, cool. But we'll do that tomorrow. We'll do that, yeah, tomorrow. Okay, we got a good amount done. Tomorrow we'll just take these areas and we might get done early. Well. Okay, but good job, y'all.